we're group one, consisting of myself, Kennedy, Jordan, David, and Alex. And today we're going to be summarizing chapter 5, which talks about dimensional analysis. So starting off with 5.1, there are two different systems that we can refer to when expressing variables in terms of basic dimensions. They are the MLT theta system and the FLT theta system. The MLT theta system has four basic dimensions, each representing one of the letters: mass, length, time, and then theta is temperature. And the same goes for the FLT theta system. However, in this case, mass is replaced by force. And then the table at the top right of the page shows the basic dimensions of different fluids properties. Dimensional analysis can be used for several reasons. One is for planning an experiment or theory and can save time and money when you have dimensionless variables. Another reason is to scale models that can then be used to represent a prototype. And the principle of dimensional homogeneity is a rule for dimensional analysis. And the Buckingham Pi theorem is a method of reducing a number of dimensional variables, both of which will be further discussed in our summary.
Okay, so 5.2, the principle of dimensional homogeneity. Dimensionally homogeneous just means that all terms in one equation have the same units. Dimensional variables are quantities that actually vary within a given case and can be plotted against each other. They have dimensions, but are also able to be non-dimensionalized. Dimensional constants, they vary from case to case, are constant in a given run, have dimensions, but can also be non-dimensionalized. Pure constants have no dimensions. They're something like pi. And then angles and revolutions are dimensionless. They have units, but no dimension. And counting numbers just have no dimension as well. And then moving on to 5.3, the pi theorem. So we have J, which is the reduction factor. It indicates how many pi variables we're going to have. And you find that by taking the dimensional variables and subtract the dimensionless variables. And each pi group must be independent of all the other pi groups. And we have two methods for finding them. We have the repeating variable method. Step one is you write the function with all the parameters involved in the problem. And then step two, list dimensions of each variable, select the primary dimensions. You would use table 5.1, which we have listed at the very top of our sheet today. And then step three is list all the parameters in terms of their primary dimensions. And then select J number of parameters from step one. J again is up here. You found that. And then step 5 is combine the variables chosen from step 4 with one additional variable that you found from step 1, and just repeat that until you've used all of the variables. And then step 6, express the final form as a dimensionless function. And we also have the other method, which is the iSpin step-by-step method. And you would just kind of use multiplication and division to try and rearrange and get a dimensionless expression based on kind of the same parameters that you listed in step 1 from the repeating.
5.4, which is the non-dimensionalization of the basic equations. We start with our Reynolds number, which is important with or without a free surface and can be neglected in regions away from high velocity path gradients. If the Reynolds number is less than 2300, it is laminar flow. If it's greater than 4000, it's considered turbulent flow. Moving on to our Euler number, when it is equal to 1, it's considered frictionless flow. And if the change of pressure involves vapor pressure P of V, it is called the cavitation number. Our Froude number is the dominant effect in free surface flows, very important in stratified flows where a strong density difference exists without a free surface. If f of v is less than 1, there is slow and calm flow. If f of v is greater than 1, it's considered rapid and chaotic flow. Our Weber number is important only if its order, unity or less, occurs when surface curvature is comparable in size to liquid depth. Our Strahl number shows measured shedding frequencies. Our Cauchy number, given as C of A equal to V squared over our Euler number. And lastly, our Mach number exerts a strong effect on compressible flow properties if it is greater than 0.3. When our Mach number is in between 1 and 5, it's considered supersonic, and if it is less than 5, it is considered hypersonic.
Moving on to 5.5, modeling and similarities. Modeling law states that flow conditions are identical if the dimensionless parameters are the same in the prototype and the model. Moving on to type of similarities, there are more, but these are just three basic types. For geometrical, it states that all dimensions are similar and it has a linear scale ratio. For kinetic, it states that motion of particles act the same in both systems. And for dynamic, the length, time, and force all have a linear scale ratio. Here is a picture of a geometric similarities. And one more comment when modeling, you must try to match some of the numbers as stated in 5.4. For example, if you try to match the Reynolds number instead of the Mach number, you might end up with a Mach number in the hypersonic range, and that's very hard to reach in a wind tunnel. Another comment is that all systems will never be truly identical or a perfect ratio because in the real world there's outside forces or even something as heat capacity, which is different of the two elements used.
Hello, we're group 1 and I'll be answering question 2. Just first off, the question states that change in pressure is a function of energy, density, speed of sound, and the distance. For this problem, I'll have the basic units in the FLT data format. So delta P is force length. Energy is force length as well. Rho is force time length. Speed of sound is velocity, so it's in length time. And distance is in length. By pi theorem, we have J equals n minus k. In this problem, we have 5 terms, so J equals 5. And we only have 4 basic units since we're not using theta, so n equals 3. Therefore, k equals to 5 minus 3, or 2. And this 2 represents how many pi terms we have. So we have 2 pi terms. Let's put T for terms. And just by inspection, it doesn't appear that we can use E, rho, and C in the same sentence or in the same pi term. So for the first pi term, we'll have delta pressure as a function of rho, C, and D. And their exponents I'll be using in Greek terms, alpha, beta, and gamma. So this equals to their basic terms. This one is for the density. This is for speed of sound. And this is for diameter, which is length. And they should equal to 0. So for the first, we'll be looking at the force terms. We have 1 plus alpha equals 0. Just put a statement, alpha equals to -1. For our time, we have 2 alpha minus beta equals 0. So we have beta equals to -2. And for length, we have -4 alpha plus beta plus gamma equals 0, where gamma equals 0, which gives us our first pi term. So pi 1 equals to change of pressure over rho c squared. And again, we could just put d to the power of 0, which is 1. For our pi 2 term, we're going to try to eliminate e. So we have e, rho, c, d. And I'll be raising these to alpha, beta, and gamma. Similar to the first portion, we have their basic units. Time squared, length, -1, gamma equals 0. So for all the force terms, we have 1 plus alpha equals 0. So alpha equals -1. For the time, we have 2 alpha plus beta equals 0. So our beta equals -2. And length term, we have 1 minus 4 alpha plus beta plus gamma equals 0, where gamma is -3. So our pi 2 term is this. And just from the pi theory, we know that pi 1 equals to some function of phi times pi 2. In this case, we have delta p over rho c squared equals 5 over rho c squared d cubed. So this is the answer for part A. For part B, I'm just going to simplify the equation a little further just to be easier to work with. So since it's one equation, we can cancel out these terms. So we will have pressure as a function of phi, energy release, and the blast radius. So for part 2, I'm going to make an assumption that the temperatures are both constants for both cases. For example, it's both 20 degrees Celsius. So that means that the densities will be the same and that the speed of sound will be the same for both. And again, just by equation, it cancels out, but I think it's a fair assumption to make. So now we have our prototype's pressure equals to our the pressure of our model. This is stated in the question. So then we have phi of our energy release of our prototype, our distance cubed equals this. So again, this is the prototype. The first, the P is the prototypes, E is the model. And just by equation, these phi's have to be same so we can cancel them. Our equation also, our problem also states that this is our model is 1/2000th of our prototype, and the diameter for our prototype is given. So plugging these in, we have this equation. Energy of our prototype over 2000. We can cancel out the energy. And just by moving these to the other side, we will get that the diameter of our model, or the blast distance of our model, is equal to this statement. If our model is a third root of 1000 cubed over 2000, which this number is about 79.37 meters. And if you want to round up, we can say it's 80 meters.